reach into a vegetable bed at the end of October and pull up 2 pepper plants. Same variety, same row, same soil, same water, same season in every way. One of them was treated 3 times with a kitchen ingredient that costs less than $1. The other was not. Hold both root balls in your hands and the difference is not subtle. One is thin, pale, almost fragile, the kind of root ball that probably struggled through every hot afternoon in August. The other is dense, dark, branching in every direction, almost twice the weight of the first. That is not a gardening story. That is a documented, repeatable, peer-reviewed result, confirmed in the journal Crop Science in a study from the University of Queensland in 2014. And the ingredient that caused it sits in your pantry right now. It costs under $1. It takes 30 minutes to prepare. And there is a very specific biological reason why you have never seen it on a shelf at any garden center in the country. A reason that has nothing to do with conspiracy and everything to do with physics.
Part 1. The part of the plant nobody measures. Most gardeners spend a lifetime looking at the wrong half of the plant. The eye goes up to the leaves when something looks wrong, up to the blossoms when the set is thin, up to the fruit when August arrives and the harvest is smaller than it should be. And the entire garden industry is engineered to meet us there. Foliar sprays, bloom boosters, calcium sprays for blossom end rot, liquid tomato food you pour on the surface. Row after row of colorful bottles designed for the part of the plant you can actually see. But there is a quiet principle that every experienced gardener eventually learns the hard way, usually after a decade or 2 of buying those bottles. Everything a plant becomes is decided underground. A shallow root system cannot be fixed from above. A plant with thin, underdeveloped roots will drop blossoms under stress whether you spray it with calcium or not. It will struggle through a dry week no matter how much you water the surface. It will produce thin fruit even when the weather is perfect because the mineral delivery system is undersized for the demand. The root is the engine, and the engine is invisible.
Here is what makes this worth your attention today. The root is also the most responsive part of the plant to targeted intervention. At 3 specific moments in a growing season, you can deliver a direct hormonal and nutritional signal to the root zone that accelerates growth, increases lateral branching, and deepens the root mass, without synthetic chemistry, without expensive products, and without anything that isn't already in your kitchen. Before the recipe, it's worth spending a few minutes on what a root actually needs to do this. Because once the biology makes sense, the ingredient makes complete sense.
Part 2. The question nobody asks in the rooting aisle. Walk into any major garden center this spring, and the rooting hormone shelf tells a curious story. Plastic tubs of powder, most priced between $5 and $15. The premium labels push $30 for a few ounces. The active ingredient on almost every label is the same compound, indole 3-butyric acid, sometimes accompanied by naphthalene acetic acid. Both are synthetic auxins, laboratory-made copies of the very hormone a plant naturally uses to push out new roots. I want to be clear, these products work. They genuinely do what they say. But they are synthetic imitations of something a living organism already produces and has been producing for free in kitchens around the world since before any of us were born. Here's the question almost nobody at that garden center shelf ever thinks to ask. If a single-celled fungus, already present in nearly every American kitchen, produces the exact same root-triggering hormones and produces them in living form, surrounded by amino acids, B vitamins, and bioavailable trace minerals, why is that fungus not on the shelf right next to the synthetic powder? The answer is not a cover-up. The answer is shelf life.
The moment that fungus is activated in warm water, it begins producing carbon dioxide at a rate that will build pressure inside any sealed container. Within 48 hours, a sealed plastic bottle of this living solution would bulge, leak, or burst on a warm warehouse shelf in Georgia. There is no preservative that can extend that organism's viability to a 6-month retail shelf life without killing the very thing that makes it useful. Synthetic rooting products have to be dead and stable. This one has to be alive and active. That single physical fact, combined with a profit margin of essentially zero for any company willing to try, is the complete reason you have never seen it in a garden center. So the recipe has always lived where it belongs, in the kitchen, made fresh in about 30 minutes by gardeners who knew what they were doing. The organism is baker's yeast, Saccharomyces cerevisiae, and what it does to the root zone of a vegetable plant is unlike anything else available to a home gardener at any price.
Part 3. 3 things yeast does the moment it reaches the soil. For generations, grandmothers used Saccharomyces cerevisiae for exactly one purpose: to make bread rise. But peer-reviewed research, published in Crop Science in 2014, in the journal Plants in 2023, and in Frontiers in Industrial Microbiology in 2024, has quietly documented a second purpose for the same organism that the bread-making world has no use for. When living yeast cells are introduced to soil at the root zone, 3 things happen simultaneously. The first is hormone signaling. Saccharomyces cerevisiae produces indole-3 acetic acid, IAA, the master signaling molecule of the entire plant kingdom. This is the chemical message that tells a root cell to divide, to stretch, and to initiate a new lateral branch. It is the same hormone class that the synthetic rooting powders on that garden center shelf are trying to replicate. The yeast also produces cytokinins, a second hormone class that drives cell multiplication at root tips, which is precisely where lateral roots originate. A 2024 study in Frontiers in Industrial Microbiology measured significantly higher chlorophyll levels in lettuce seedlings treated with brewer's yeast and traced those gains directly to the auxin and cytokinin produced by the living fungus. Real hormones, living source, delivered directly to the root zone by something that costs 60 cents. The second is a nutrient delivery. As yeast cells multiply in warm sugar water during the brewing window, they release amino acids, peptides, B vitamins, and trace minerals, nitrogen, phosphorus, potassium, magnesium, iron, zinc, directly into the surrounding solution. These are not raw, locked-up minerals that a root must work to break down. They are already in the pre-digested, bioavailable forms that root hairs can absorb almost on contact. It is the closest thing in nature to a direct feed for a plant under transplant stress. The third is microbial competition. Yeast cells settling into the root zone physically occupy space. They compete with soil-borne pathogens, including some damping-off fungi, for nutrients and attachment points. Studies on lettuce and tomato root zones noted lower incidence of certain harmful pathogens in yeast-treated soil, attributed partly to that competition for space and partly to antimicrobial peptides the yeast secretes as it grows. 3 effects: 1 teaspoon of pantry shelf powder, hormone signal, nutrient delivery, microbial competition. And then there is a 4th effect, the one that surprised plant scientists most when it was first observed under a microscope. This is the part that takes the story from interesting to genuinely remarkable.
Part 4. The 2010 discovery that changed the textbook. For most of agricultural science's history, roots were understood as passive structures. Straws, essentially, inserted into moist earth, drawing up dissolved minerals as water moved past them. The image was of absorption, minerals dissolving in water, water carrying them upward. That picture was largely undisputed for over a century. Then in 2010, Dr. Pongfulo Hinian and her research team at the University of Queensland aimed a confocal laser scanning microscope, a fluorescent imaging tool that renders living biological processes in real time, at a young tomato root growing alongside living yeast cells. What they saw?
was not absorption. The root was eating. The root tip cells were actively engulfing the yeast cells, pulling them inside, into the space between the cell wall and the cell membrane, a zone normally reserved for the plant's own internal processes. Once inside, the plant cell produced a controlled burst of superoxide, a precise oxidative pulse that stripped the yeast's outer wall and made everything the yeast had accumulated in warm sugar water directly available for absorption. Nitrogen, phosphorus, stored proteins, the complete nutritional contents of the yeast cell extracted directly into living root tissue. And then, something stranger still. Some of the yeast cells survived this process. They emerged back out through the extending root hairs. They rebuilt their cell walls in the surrounding soil. They gathered new minerals from the earth around them. And they were eventually consumed again. This process was formally named the Rhizophagy Cycle.
From the Latin and Greek, root eating. Since 2010, this has been confirmed in dozens of follow-up studies across multiple plant species, both monocots and dicots. The 2014 crop science paper demonstrated the same nutrient uptake in sugarcane and tomato using both living and heat-killed yeast cells. What this means for a vegetable gardener preparing for the spring season? A tomato root is not a drinking straw. It is an active harvester, an organism that pulls living microbes inside its own tissue and extracts nutrients directly from them. Yeast is one of the few organisms common enough, safe enough, and inexpensive enough that any home gardener can supply it deliberately, strategically, at exactly the moments the plant needs it most. The plant does the rest of the work entirely on its own.
Part 5. What the research actually measured. A few minutes on the actual numbers, because this is where a lot of gardening content goes wrong. The mechanism is real, the research is real, but inflated claims set up expectations that a real garden can't always meet, and that kind of disappointment puts people off something that genuinely works. So here is what the studies actually reported. In the original 2014 Queensland study published in Crop Science, yeast-treated tomato and sugarcane plants showed significantly higher root biomass compared to untreated controls after 4 to 10 weeks respectively. Nitrogen and phosphorus content in root and shoot tissue was substantially elevated. The root-to-shoot ratio increased, meaning proportionally more root mass per unit of above-ground plant. That is the number a vegetable gardener actually wants. A 2023 study in the journal Plants, testing auxin-producing yeast strains isolated from traditional Mexican maize varieties, found that the 4 highest-performing strains produced a 1.5-fold increase in plant height, fresh weight, and root length compared to untreated controls. No synthetic chemistry, just living yeast inoculated at the root zone. A 2024 paper in Frontiers in Industrial Microbiology, using residual brewer's yeast on lettuce and tomato seedlings, documented measurable improvements in germination rate, leaf number, fresh weight, and chlorophyll content, at a yeast concentration of approximately 10 million cells per milliliter. Those are the real numbers, not a doubling overnight, not a transformation after a single application. A measurably larger root mass, higher mineral content, better establishment, and at the end of a full season with 3 well-timed applications, a root ball that is often 2 to 3 times
denser than the untreated plant of the same variety. The lab measures the mechanism, the garden confirms the scale. Now, the recipe. Before we get into the steps, a quick word. Everything in this video, the science behind the Rhizophagy cycle, the complete recipe, the 3 application windows, a plant-by-plant response guide, and a full troubleshooting table, I've put it all into a written guide you can keep. It's called The Underground Garden, the complete biostimulant system for the home vegetable gardener. It's a downloadable ebook. The link is in the description below this video. If you are the kind of gardener who likes written instructions in hand when you're working outside, rather than a phone propped against a watering can, that guide has everything laid out step by step, organized by plant and by season. Link is below. Now, the recipe.
Part 6, the 30-minute kitchen recipe. 3 ingredients: 1 liter of non-chlorinated water, 2 tablespoons of plain dry baker's yeast, roughly 2 standard packets. 1 tablespoon of plain white sugar. Any pantry, any season. Total cost, depending on your yeast brand, somewhere between 60 cents and $1. Step 1 is temperature, and this is the step where most home attempts quietly fail before they start. The water must be lukewarm. The accepted activation range for dry baker's yeast is 105 to 115 degrees Fahrenheit. That range is published by Bob's Red Mill and Fleischmann's, both in their yeast guides. No thermometer needed. Touch the back of your wrist to the outside of the jar. The water should feel warm and comfortable, not hot enough to flinch from. If you see steam rising from the surface, the water is too hot and the yeast will be dead before it starts. If your kitchen runs cool, here is the simplest method I know. Boil a full kettle. Pour the boiling water into a clean glass jar. Leave it on the counter for 15 minutes. It will fall into the safe range on its own. No guessing. Step 2 is dissolving. Use a glass jar of at least 1.5 liters. You need room for the foam. Pour in the warm water. Add 2 tablespoons of yeast and 1 tablespoon of sugar. Stir gently with a clean spoon until everything dissolves into a slightly cloudy beige solution. A word on the sugar, because this is the part that confuses people most. Plant roots have no use for refined white sugar. The sugar is not going to your garden. The sugar is the wake-up signal for the yeast, the energy source it needs to begin multiplying and releasing hormones into the water.
By the time the diluted solution reaches your garden, the sugar is essentially gone, consumed entirely by the fungus during the 30-minute brewing window. Step 3 is covering, and this one matters more than it sounds. Do not seal the jar with a tight lid. As the yeast activates, it produces carbon dioxide gas rapidly enough to build dangerous pressure inside a sealed glass container. A sealed glass jar will crack on your kitchen counter, sometimes within hours, without any warning. Cover the opening with a clean paper towel held in place with a rubber band. The CO2 escapes safely. Dust and insects stay out. The jar also goes in the dark. A kitchen cupboard, a closed pantry shelf, or even a folded dish towel draped over the top. Direct sunlight delivers ultraviolet light that damages yeast cells before they finish their work. Step 4 is simply waiting. During this window, the yeast is multiplying rapidly, consuming the sugar and releasing its hormone and amino acid payload into the surrounding water. 2 visible signs that the brew is ready: a foamy beige-colored cap forming across the entire surface of the liquid, and a steady stream of tiny bubbles rising through the jar. The smell is mild and bread-like, familiar to anyone who has ever proofed yeast for a loaf of bread on a quiet morning. When the foam cap appears, the concentrate is alive and ready.
Part 7. Dilution, timing, and where to pour. One final step before it reaches the garden. The concentrate is too strong to apply directly. At full strength, the yeast population is dense enough to briefly disrupt your existing soil microbiome and cause osmotic stress to fine root hairs. The dilution ratio is not optional. 1 part concentrate to 10 parts water. Stir the 1 liter brew into 10 liters of plain, non-chlorinated water. Tap water left uncovered in a bucket for 24 hours works well. That window is long enough for chlorine to evaporate. Collected rainwater is ideal. Apply only to the soil, not the leaves. Pour slowly and deliberately at the base of each plant. Aim for soil penetration to about 6 inches depth without pooling or flooding. A mature tomato or pepper plant needs roughly 1 liter of the diluted solution. A seedling or fresh transplant needs only 1 cup. Now, timing. This is the part that separates a one-off experiment from a system that actually changes the harvest. The yeast mixture is not a weekly liquid fertilizer. It is a strategic biostimulant. It is most effective and most important at 3 specific moments in a plant's life, when the root system is under the most stress or facing the most demand. Window 1 is a transplant. The moment a young plant moves from a starter tray into open garden soil, the root system enters a period of real stress. The soil is unfamiliar,
The bacterial population is different, and the temperature may be several degrees warmer or cooler than the pot it came from. Delivering yeast-produced auxins to the root zone at this exact moment supports rapid lateral root expansion and measurably reduces transplant wilt. Plants treated at transplant tend to hold their leaves firm through afternoon heat within the first week, rather than drooping for 10 days while the roots establish. Window 2 is at the very first sign of flowering. This is the moment the plant makes one of its most consequential decisions: how much energy it can commit to fruit production. A root system that is deep, dense, and well-branched at this stage means more flowers supported to full fruit, fewer blossoms dropped under stress, and more consistent pollination. This single application may be the most directly influential on final fruit count. Window 3 is when the first small fruits become visible. The plant is now in maximum mineral demand mode, pulling calcium, phosphorus, potassium, and magnesium in high volume to swell each fruit. A wave of yeast-released amino acids and bioavailable trace minerals at this stage supports that demand directly, without forcing the root system to strain beyond its capacity. 3 applications, spaced naturally across the growing season. That is the entire system. Applying more frequently than 3 times risks tilting the soil microbial balance in the wrong direction. Applying fewer than 3 misses the windows where the effect would have been most meaningful.
Part 8. Honest expectations and the mistakes that ruin the brew. A word about expectations, because this is where gardening content tends to lose its credibility. A single application of yeast water will not rescue a struggling plant overnight. Within the first week after a transplant application, the plant tends to hold its leaves more steadily through afternoon heat. That quiet stiffness is the first visible signal that new root growth is beginning. Within 2 to 3 weeks, new lateral roots have branched and the main stem will visibly thicken. By the end of the growing season, the difference is most clearly seen not in the fruit on top, but in the root ball below, often 2 to 3 times denser and more fibrous than an untreated plant of the same variety grown in the same conditions. That end-of-season root pull is the result this method is known for. 5 mistakes that quietly ruin the brew before it ever reaches the garden. Mistake 1, water that is too hot. Anything above 120 degrees Fahrenheit kills the yeast on contact. The brew will smell sour rather than bread-like. If that happens, discard it, cool fresh water, and start again. Mistake 2, a sealed lid. Never. CO2 pressure cracks glass jars on the counter without warning. Paper towel and rubber band only. Mistake 3, expired yeast. A packet more than 2 years past its printed date may no longer activate. If no foam appears within 40 minutes, open a fresh packet. Mistake 4, storing the diluted solution. It does not keep. Use it within 24 hours of mixing. After that, the yeast population crashes, fermentation shifts toward alcohol production, and the result can mildly stress root tissue rather than support it. Mistake 5, applying during the hottest part of the day. Always apply in early morning or late evening when soil temperatures are moderate and the root zone is not already under heat stress. Plants that respond most strongly: tomatoes, peppers, eggplant, cucumber, zucchini, and corn. Strawberries respond well, particularly during the runner stage. Leafy greens show clear gains at the seedling and transplant phase. Root crops benefit most from the early establishment window only. Established fruit trees and perennials respond more slowly, but show measurable improvement in new feeder root density when treated in early spring as the growing season opens.
There is something quietly satisfying about a garden recipe that comes from the back of the pantry rather than a plastic jug. The same yeast that has made bread rise in farmhouse kitchens for generations can make a root system reach deeper, branch wider, and carry a heavier harvest. The science has been there since 2014. The ingredient has been on your shelf your whole life. The recipe? 3 applications, 3 windows in the season. That is all it takes. If you want everything in one place, the full recipe guide, the 3-window timing calendar, the plant-by-plant response chart, the troubleshooting table, and the dilution reference card, it is all in the Underground Garden, a complete printable ebook available through the link in the description below. And there is a second homemade preparation I want to show you, one that works through a completely different mechanism and pairs naturally with what we covered today.
Used at the right moment, it measurably increases flower set and holds more blossoms on the plant through heat stress. That one is coming in the next video. Until then, may every root in your garden run deep, and may the harvest be as heavy as it deserves to be.